Everybody is fine after the lunch, and I'm happy to open the second track about SSL. We have here with us Tal from Imperva, and in my youth I was a great fan of the film noir, the Black series in Hollywood, and there was an eternal rule due to the Hollywood codex and censorship: crime doesn't pay. Even not a perfect one. Is this true? Please tell us.
Well, I guess only time will tell. And so I hope in 40 minutes time we'll be smarter about crime and is there a perfect crime and whether or not it pays and in which currency. So let's start. What we're going to discuss today, we'll start with a brief introduction. So we would all have a common background on compression, and also we'll take a second look at the crime attack, already mentioned in a few talks here. Then we will move to expand crime in two different directions. One direction is by increasing the attack surface, by applying the crime attack to HTTP responses, where the original crime attack was attacking HTTP requests. And secondly, we will show the time attack, which really helps the attacker to drop the precondition of being a man in the middle or being an eavesdropper, and replacing that precondition with just the ability to measure times, which can be achieved by a JavaScript, and therefore the attacker does not have to be an eavesdropper. So let's talk about the attack surface to begin with. So where do we have a compression on the web? And this is was the situation before the crime and the changes that were made as a result of it. So compression over the web is largely based on the gzip algorithm, and the most common compression, when you tell someone HTTP compression, naturally you would probably mean the HTTP response body compression and not something else. But there are some other less common compressions, such as the HTTP request body in post requests, some clients support that, and also some header compression that in certain cases, such as when the whole SSL channel is compressed, which was supported by Google Chrome until recently, and also in Speedy, sometime dubbed as HTTP 2.0, which has large support over clients, all browsers except Internet Explorer, but not so much on servers. So the main use case for compression over the web is for HTTP responses. So let's take a deeper look at the gzip compression. It's really a two-step compression process, combining two algorithms together to combine the LZ77 to compress recurring string, and Huffman coding to compress frequent symbols. And gzip was made the compression algorithm of the web, probably because it achieves a good balance between the compression rate and the performance and the resources needed for the compression. So LAMP-LZ compress repeating strings. This is LAMP-LZ, it's the LZ and LZ77, which is that algorithm was proved to be asymptotically optimal. And one interesting feature of it is there is no overhead. There are no extra dictionaries transmitted between the sites. And it's best explained with an example if we take the first two verses of the Genesis. So we can see that in natural language, if we can call Genesis natural language, then there is a lot of repetition of strings. So instead of coding the second space equal space the and then space, in the beginning God created the heaven, so I can code the second the as a pointer to the previous one, and by that I will compress that input. And we can see as the text is getting richer and bigger, there are more recurring strings, and the better compression it achieves. And the other part of the gzip compression is Huffman coding. Even if we compress all recurring strings, there's still redundancy in the text, in the sense that some letters are more frequent than others. For example, the E letter is very frequent is the most frequent letter in English compared to Q. So I would probably be better off if I could encode E with fewer bits at the expense of coding Q or Z with more bits. And our main interest in compression will be focused around the LZ of algorithm of compressing recurrent strings, but we still need to say something about this Huffman coding, because it will kind of will be troubling for us, because as a result of this coding, the symbols are not necessarily byte aligned, and some of them will be shorter than a single byte, which kind of might be a problem for us in later stages. We'll talk about it. So let's talk about the relationship between compression and encryption. And so there is compression, there's encryption. So we need to compress the data to save bandwidth on the one hand, and on the other hand, we want to compress it to protect its privacy. So what should we apply first? Should we compress and then encrypt, or encrypt and then compress? Of course, we need to first compress, and only then we can encrypt, because encryption really conceals all the redundancy within the original text, and applying compression on encrypted data does not help. And if someone tried to compress once an encrypted file, you would see that the compression was not very successful. So it was detected as early in 2002, actually, in a scientific paper, that compression can leak some information about the plain text. And this was very early compared to a decade ago, which is infinity in the terms of security. And it was independently rediscovered by Rizzo and Duong. But Rizzo and Duong were also pioneers in the sense that they showed that this theoretical problem is very practical and relevant to our actual web environment. And they dubbed their attack as CRIME, Compression Ratio Info Leak Made Easy, which is a chosen plain text attack, and we'll talk about that, and targets compression information leakage. So what is it? Chosen plain text attack. The attacker has the ability to choose arbitrary plain text to be encrypted and obtain the corresponding ciphertext. So Eve can tell Alice what to send to Bob, and then Eve's also an eavesdropper and get to see the encrypted message traveling through the wire. So this is the attack model. And what CRIME is trying to do, we'll give first the intuition, then we'll get some more rigorous description. So the attacker, this is a chosen plaintext, tell the victim to send something to the web server, and this the attacker tells the victim to do so with a JavaScript, and the this text contains some guess of the attacker about the secret part of the text, and as we said, the LZ part of the compression will compress identical strings. So if the attacker guess was correct, then the result will be that the payload will be better compressed, will have shorter length, and the attacker will be able to observe it since he is or she is man in the middle, or eavesdropper. So in a more rigorous description of this, so the attacker starts with initial guess with some kind of non-prefix of the secret string, and then tries to append every letter within the alphabet and observe the results of the payload size over the network. And for the correct guess, then the result will be shorter than all other guesses. And this process can be applied in repeated manner until the whole secret is revealed. And if we take it into the web environment, then attacker is an eavesdropper and can see the ciphertext over SSL. And the attacker creates an HTTP request interactively with JavaScript, and the attacker has almost full control over the URL and can predict most of the header, but the attacker does not control or see the cookies because it doesn't see them on the wire because they are encrypted, and it cannot access them through the script because of the same origin policy. So let's just show an example. So the attacker will do something like post or get session ID equals A, and then B, and then C, and so forth. And when the session ID equals D is a repeating string within the cookie, then the payload will be compressed in a more successful way, and resulting a shorter payload over the network, and the attacker will be able to observe it, and then the attacker will know that D was the correct guess and can move on to guess the next character until the whole cookie is revealed. And this is really what this slide showed. This is one of the slides, the original slides of Wang and Rizzo from last year. So there is a little problem here with the Huffman coding that we had mentioned earlier, because sometimes we cannot detect a good guess because when we add a character that is very frequent, even if it's not a correct guess, then the Huffman coding will compress it, not because of the LZ, not because of it being a recurring string, just because it is a very common string, a very common symbol that can be compressed better. So in order to really differentiate between the different effects of the LZ algorithm and the Huffman coding, the attacker can send two requests, and just changing the order of the symbols, and the algorithm is very sensitive to changes, while the Huffman coding is not, the context is not relevant. It just cares for the distribution of the symbols. So in that, using that, we can eliminate that effect of the Huffman coding. So as a result of this research, speedy implementation, cancel or modify header compression, and Chrome disabled SSL compression. So there is no request compression, and therefore no more crime, since there is no attack surface. So let's start by resurrecting crime and applying it to responses, so it will have some attack surface. So what do we have to do in order to transform crime from attacking requests to attacking responses? So the encryption and compression algorithms are the same, and of course we're changing the secret element location from the request header to the response body, which is okay. So we still need to figure out three things. We need to find a secret element, which was the cookie value in the previous crime attacking requests, and this secret should have some kind of prefix or suffix, so we will have an initial guess for us, and this is maybe the most important and the hardest issue of all. The attacker needs to control some part of the response, so it can be compressed along with the secret. But in the case of request, it's very trivial because the attacker directly controls the URL. But in the responses, the response comes back with the server, so it's not very obvious how the attacker can control the server's response and include some arbitrary text within it. So let's start with the easier issues. So luckily, there are many secrets in responses. In fact, most of the secrets of the applications are found in their responses. Think about your bank balance. It appears on the response, right? And they are often very structured. Again, let's take the bank balance example again. So your bank might tell you, this is your bank balance, and then the amount will show up. So usually the secrets are structured. So it's not too hard to find structured secrets, although there are many of them, but we have to remember that now they are application specific. You know, for the bank, it will be your bank balance, and for Facebook, it will be, I don't know, something else, maybe your Facebook ID or something like that. It's not like the case where in crime that you always could aim for the cookie. And so we are left with finding the last element of chosen plain text location, which was the URL for taking a request. So we found out that, well, after we find out, it's very natural to think that we would find that, but many applications embed user inputs as expressed with HTTP parameters within their response. And in fact, many websites embed elements from the request in their response, even if they were not expecting such elements in the request. For example, we can see here at the bottom of the screen that Twitter, if you append some random parameters as x equals mic string, then this input will be embedded within the response. So the attacker can control and put some arbitrary strings within the response. So we have all the ingredients, and we can cook ourselves some crime attack on responses. And for example, we try to do the same with the Google Scholar and trying to find out the secret username, and by putting some parameter, guessing parameter over the URL, and we were able to do so. And as this video shows, that we started with the suffix that time from @gmail.com, and our algorithm is guessing the full email of the victim in a character by character fashion. So let's move on, but eventually it will get the whole email. So let's sum up the advantages and disadvantages of moving the attack from the from the request to the response. So HTTP response body compression is very common practice as opposed to request compression, and it's part of the building block of the internet, not something you can easily turn off. And this is more of a philosophical, if you like, argument that when you're attacking the data in the response, you're attacking the secret data itself and not some kind of intermediate, a cookie or so. But there are also disadvantages. For example, the user input must be encoded before it gets embedded into the response. If the website does not properly encode it, then it will have some grave issues of course scripting and so forth. So the attacker alphabet is really limited to alphanumeric sort of text. So the attacker can only guess alphanumeric secrets, and the environment is less sterile. For example, response body might be altered due to other reasons. We saw responses that included the date and the time and so forth. So it's when you have more processes that really changes the size and the plain text of the text, it makes it harder for the attacker to really say which of his guesses were correct, because it doesn't know if the payload is smaller because the guess was correct or because something else changes the plain text. So so responses are much less sterile than requests. So let's move on to our second improvement of the crime algorithm, and this is the time attack. And as we recall, crime attack model, the attacker needs to be both an eavesdropper and have control over the web page the victim visits in. So having control over the web page the victim visits in, it's not so hard, but being able also to observe its traffic with another site, this is a different matter. And usually, to be an eavesdropper, you need to be in some physical proximity within your victim, for example, in a unencrypted wireless LAN, or app poisoning over a local network, and so forth. So it's a rather big limitation, and it would make the attack more practical if you can just drop that limitation. So what we had presented back in Black Hat Europe this year, the time attack, the timing infolic made easy, the successor of crime, and really let's try to follow it's kind of complex argument, but we can break it down to three more simple arguments. So first, we have to establish that the HTTP payload size may carry sensitive information. And in fact, we only need to show that payload size differences carry that sensitive information, which is kind of what this crime is all about. That's what we've shown, that being able to detect small changes on the payload size is the key. This is what the attacker is doing with the crime attack, and by detecting these small differences, the attacker is able to determine which of the guesses of their guesses is the correct one. And after that, we established that the small differences really of payload size really carry sensitive information. We'll show that using timing measurements, the attacker can distinguish these payload size differences and therefore extract the secret within them. And finally, we need to show that these timing measurements can be carried out by a JavaScript. So if we will show all of these three different elements and combine them together, we will show that using a JavaScript, the attacker can detect the secret information that is carried over the payload size differences. And if it can be done with a JavaScript, then the attacker needs not to be an eavesdropper and just can give that JavaScript to the victim. So this is a different. This is chosen plain text attack model, but without eavesdropping ability. Eaves is no longer an eavesdropper. So let's talk about sensitive information in HTTP payload size. So we had seen that the attacker can find out about secret information just looking at the different payload sizes over requests and responses for the crime attack, but it's not necessarily directly only connected to the crime attack. For example, if we take again the bank balance page, we'll take another look at it. And let's say that everything is constant within this page except the number of digits in your balance. So we all can agree that the number of digits I have in my balance is sensitive information, and you know, attacker would like to know if he's attacking a victim that has only 1 digit in its bank balance or 9 digits in its bank balance. So this is sensitive information, and let's say there is no compression and so forth. So if we can detect just the difference in this payload, and we know that the constant factors are, let's say, 1 kilobyte, and the rest is just the digits in your balance, then I can just by comparing the different results, I can learn if you have 8 digits in your bank balance or just 1. So we had seen that this payload size is not revealing secret data, is not only related to the crime attack. And so I think that's enough to, I hope it's enough to convince you that payload size differences is sufficient to extract the sensitive information. And now we move on to see how we can do it just by timing measurements. So the intuition is pretty clear. The first thing that's on Google developer website is how to make the web faster, minimize the payload size. So size and timing are very much related to one another. And Google web page even give another tip for developers and says, in addition to the network cost of actual bytes transmitted, there's also a penalty incurred for crossing an IP packet boundary. And when we hit the word boundary, we understand that this is something we can use, because when you cross a boundary and you pay, suddenly you pay a fine. You don't just pay linearly, but you get an extra fine for crossing an IP packet boundary. Then there's something we can use in order to, as attackers, in order to detect changes in payload sizes. So a more accurate saying will be that you pay this fine when you cross some TCP window value. So because client sends a window of packets and wait a round trip time, RTT time, for acknowledgement. And this acknowledgement time, this round trip time is very noticeable. And therefore the attacker can easily distinguish between payloads that their size are smaller or equal to the window, and even if they exceed that window, even with 1 byte, then they will pay an extra round trip time fine, and then the attacker will be able to detect it just by measuring timing. And let's see this phenomenon with Chrome. So Chrome sends 2 packets and then wait for round trip time. And if you need to send 3 packets, you pay extra round trip time, as we can see there in the red rectangle here, that you wait almost 170 milliseconds more for the acknowledgement to arrive before you can complete, the client can complete its request and send that 1 extra byte. So it's very noticeable. And the same goes for the response, and this is recording a pickup of Apache, and again, every 3 packets that Apache stops and waits for acknowledgement. This time it takes it, the round trip time was around 180 milliseconds. So we had seen that small differences can create big differences with timing. Now it just remains to see if we can capture all of it using just by using a JavaScript. So what we'll do we'll create, for requests, we create an XHR request, XML HTTP request, and we don't care for the responses. We just want to get the request out, and we use the get time function of JavaScript and on already state change, so we can time the time for the request. And noise elimination, because timing is very sensitive to noise. For example, if there is some delays over the network, then it changes your measurement. But if you take enough measurement, you can cancel that noise. We cancel it by repeating each request 10 times, and then obtaining the minimal time of it. And so let's see our results. On the left-hand side, you can see the results from the web developer console of Chrome, and the right side you can see our script results, and with alternating sizes. Here we send alternatively sometimes 2,515 bytes, and on the other request 2,001 less byte, and then we minimize. We take the minimal value of all these 10 requests, and we can see that timing can be correctly captured. Our results with JavaScript are very similar to the results that are obtained with the developer console, and the results are conclusive, and we can easily detect using the previously discussed timing boundary that extra round trip time. We can easily detect it with JavaScript. And this was for requests. We can apply a similar logic for responses. First, we try to do it with by loading iframes, but this was foiled by the X-frame option headers that was meant to block clickjacking. So not all sites implement it, but some sites do. But if you take something that does not adhere to the X-frame option header, for example, if you load an image, so the image will be fetched, and you will receive the image response, and only then the browser will tell you, well, this is not an image, I'm not presenting it, but it will travel over the wire and will get compressed and so forth. So we get the payload that we need, and we can measure its time. So let's revisit our argument about the timing attack. So we had shown the HTTP payload size may carry sensitive information, and moreover we showed that HTTP payload size differences is sufficient to detect. You don't need the absolute value of the payload size. And using timing measurements, attacker can distinguish HTTP payload size differences because of that boundary effect of the TCP window, and these measurements can be carried out by JavaScript. So collapsing all these different arguments together, so the attacker can give the victim that JavaScript that will measure the timing and will detect the differences in timing, and therefore the attacker no longer needs to be an eavesdropper, and by thus making that attack even more practical. So what can we do to prevent this kind of attack? So let's start. So let's conclude what we had seen here. We had shown we showed two different improvements to the crime attack. One was related to applying it to response and not to request, and the other one was to extending it so the attacker no longer needs to be an eavesdropper. And as we said, it's not this payload differences attack are not necessarily related to the crime attack, as we had seen, for example, that bank balance, even if there was no compression, then this sort of vulnerability exists in this web page. So what wouldn't work? So an instinct reaction will say, okay, if the attacker is measuring timing, then we'll just add some random time delays. But of course, as this was the reaction for the discovery of the Lucky 13 attack, and of course, adding some random time delays is not so hard to the attacker to cope with, as they can just launch some more requests and average out this random time delay. So adding random time delays wouldn't work. What would work? If browser could support and respect X-frame options to all content inclusions and not just iframes. If you could control the way that your resources will be shown for all resources, not just for iframes. And so what should application owners do? They should implement CISA protection, use the X-frame option header where possible, beware of unknown parameter, as which shown with Twitter, because the attacker needs somewhere to put his own input in order to, so it will be included in the response. So we've shown in the Twitter case that it happens even for parameters that you are not expecting to see. So it's very important to detect the use of unknown parameters, new parameters, and deploy anti-automation measures. As well, Angela actually hates CAPTCHAs, but it was in Google case when we attacked the Google Scholar, then in some cases we triggered Google's anti-automation policy, and it actually blocked us with the CAPTCHA. So this is a good example of good use of CAPTCHA when it only disturbs the bad guys, which were us in this case. So well, maybe CAPTCHA is bad, but currently it's one of our best solutions for anti-automation, and when it's being used right only for users that create a lot of traffic, then it's acceptable. So with that I conclude. If there are any questions.
Tal, thank you very much for your talk. Now I understand your introduction, only time will tell.
Okay.
Okay, any questions? Sebastian, the expert for timing attacks.
Okay, this is more like an understanding question. So, what's your attacker model like? So, because, I mean, yeah, how do you? Isn't it just a coincidence that response is like just at the boundary of that window size? Mm-hmm. It's just a coincidence.
No, it's just because one of the preconditions for the attack is that the attacker will be able to include some part that that he or she controls, right? Regardless of the timing boundary, so it will be compressed. So the attacker can artificially expand it and put it exactly on the boundary of a window. Yeah, this is a good question. So it needs to have that ability.
Okay, just one more question, sorry. What is the, I haven't seen it in your slides, what's the difference to the breach attack that like Prado presented at Black Hat this year in the States?
Yeah.
Are theirs?
Okay, there's a hidden, unhide. So
did you compress it
Okay.
No?
So this
just-
is a bit of a timeline. So we had mentioned the 2002, the original paper, scientific paper, and crime in 2012. I had presented all the contents of this talk were given in the Black Hat Europe on March 2013, and it was rediscovered by Gluck, Harris, and Prado on recent Black Hat, and we approached them, and they they didn't know our work, and they gave us credit for that. But you know, it's good for everybody that this kind of attacks get noticed. So thank you for that. And if there are more questions, I will be probably at the Impeva booth with Eckhart there, so you can drop by and ask questions and say nice things about my presentation if you like. So, thank you very much.
Thank you, Todd.